Hello there, and we're going to try now another little experiment, one you can do at home. This is latent heat. Now steam, bit dangerous. Ice, very simple. So we're going to do the latent heat of fusion, which is the amount of heat it takes to melt 1 kilo of ice. Now we're not going to have to melt a whole kilo, we scale it up. So we have to look at all the possible things we can find in our house and use them. We got ice. We might not have a calorimeter with lagging, which we've got at school. I have one of these because I stole it from school. Tell no one. But what we do have are travel mugs. This one from some institution, I have no idea who they are. Anyway, it's a convenient mug. It also has a convenient hole in the lid, which I'll explain to you later. So, what I'm going to do is, I'm going to put water in the mug, measure its mass using the digital kitchen scales. Very useful piece of kit. I'm going to take its initial temperature with a thermometer. Now, I have to get the temperature of the initial fluid into the range of this thermometer. This is designed for the human mouth. So obviously it'll have to be quite a hot temperature. Normally, I would have it only slightly hotter than the room, so that the final temperature was slightly lower than the room. So then any heat which it would gain below room temperature will be balanced by anything it would lose above room temperature. And that's the general way you do this experiment. You try to have it go from above to just below, or from below just to above, so that there is a balance between losses and gains above and below room temperature. But I'm not going to be able to do that because of the range of the thermometer I'm using. So what I'm going to do is I'm going to add warm water to my travel mug until it's almost full. And almost full, so I can take the lid, fold back the hole and insert the travel thermometer so I can read it without taking the lid off. Then I'm going to put in crushed ice and see what happens. Right, so now I'm going to add the water to the beaker. First of all, I put the beaker onto the scale and set it to 0. Because the beaker's insulated, I have to assume that it will gain no heat during this process. That it will gain no heat and it will insulate, and so no heat will be lost. I have to assume that. Now, if you have a polystyrene cup, that's even better. These travel mugs, though, not so bad. Okay, so I'm filling this up until I can actually see the water at the top. There we go. Pleasant sound. Leaving barely enough room for the ice to go in, because I'm only going to use 1 or 2 cubes of ice, so it's not going to have a huge effect on the size. Now, blood temperature, that's a bit warm, so we'll wait. And we'll wait a bit more. You want it just blood warm. We have to wait for it to cool. Or we could mix in some cold water. So now I have some cold water. I'm going to add it until I can see the top. The point is, of course, that you're trying to get it near enough so that the thermometer can be inserted through the bung at the top. So now I take the reading, 364 grams. So that's the mass before, 364. Now I want the initial temperature. And I can see the temperature is 39.8. So, the initial temperature, 39.8 degrees C. So, next thing, of course, is the ice. Now, I've taken some heart-shaped cubes because the red matches my shirt, okay? And also because the next stage prepares you for what's going to happen to you in life. First of all, you wrap the heart-shaped in some tissue paper so that you don't get it all over the kitchen, and also so that the ice will be dried. We now have to crush the ice. We have to crush the hearts. Get used to it! That feels better. Now, the crushed ice is inserted, dried in the paper. We dry it so that no water gets in, which has already lost its latent heat. Remember, we crush it so it's all at the same temperature. A large lump of ice has, the temperature on the outside is different from the temperature on the inside. So I have to reinsert back on the weighing scales, look at the temperature, twirl it round, wait for the temperature to fall. Still waiting. The temperature has bottomed out at 34.5. So the final temperature is 34.5 degrees C. And now I just need the final mass so I can find out how much ice I have added. And the final mass is 379 grams. So, I have all the information I need to be able to calculate the latent heat of fusion of ice. So, why don't I do that? So, in any heat experiment, what you're looking at is heat lost must be equal to heat gained. Now, what has lost heat? Well, just the water. There was no calorimeter. The insulated container, or styrofoam cup, doesn't lose any heat and hopefully prevents heat loss as well. Prevents, I think I said. I did. What's gained heat? Well, the ice. First by melting, and then after it's melted by going to the final temperature. So for the water we need one term, mass of the water, C for the water, that's specific heat capacity of course, change of temperature for the water. So mass, specific heat capacity, change of temperature. For the ice, we have that formula we never know how to remember. If only there was some easy way of remembering that formula, gosh, it would be so much easier. This is the ice melting. This is all about melting, folks. After it's melted, the ice has to go to the final temperature. By now, of course, it's water. So, the ice has changed temperature as well. So this is the mass of the ice, specific capacity of water, now that the water from the ice is heating up, and this is the change from 0 to the final temperature. So let's put some numbers in this. Because everything's mass on all sides, we don't have to worry about conversion to kilograms. We can convert to kilograms, and I'll show you how they cancel anyway. So what was the initial mass of the water? Well, as we zeroed the scale, the original mass of the water was 364 grams, which of course we divide by 1,000 to make into kilograms. The specific heat capacity of water, 4180 joules per kilogram per Kelvin. And the change of temperature of the water, well, that's easy enough. You can do that in your head, can't you? It's 5.3 degrees. Now, the mass of the ice, on the other hand, is the difference between the mass before and after. Again, I don't think that's a major challenge. It seems to be 15 grams. LF is our unknown. This is the ice when it's already water, so it's 15 grams, specific heat capacity. And the change of temperature for the ice, well, as we crushed it so that it was all at the same temperature and then dried it to make sure there was no water getting in, it would spoil our results, we know that the ice must have changed temperature from 0 to 34.5. So that's 34.5. Again, I can divide by 1,000 to put these into kilograms, but then, because they're in every sum, I can then cancel them and I don't have to worry about them mathematically. Now, I just have to use the calculator. Unfortunately, in this calculator, I don't think you can see the display on the screen. I will put it in shot just in case I'm proved wrong later. But this is 8064056. This is 15 LF. And this number is 15 times 4180 times 34.5. And that comes out at 2163150. Now, it's simple maths. If I move this number to this side, I have to subtract it. So I now have 8064056 minus 2163150 equals 15 LF. So I need to subtract the two of them. 8064056 minus 2163150 equals 5900906. And to get LF, I have to divide by 15. And the answer comes out at 393393. Oh my God, it really does. Okay, and that, because it's a latent heat, is joules per kilogram. Now that's a pretty good result. Now you try and send me your page of results and some pictures of you actually doing it.